Greetings of the day. My name is Amog Upadhyay and my branch is Electronics and Computer Engineering.
My name is Sumit Kurana and my branch is Electronics and Communication Engineering.
My name is Harmandeep Singh and my branch is Electronics and Computer Engineering.
And we all have made a project on neural machine translation under supervision of Dr. Manu ma'am and Dr. Anil sir. So before explaining the whole model, I'll first likely to explain what machine translation is. So machine translation is converting source text in one language to text in another language. However, I have implemented neural machine translation, which is a proposition to machine translation that uses an artificial network to predict the probability of sequence of words, typically modeling whole sentences in a single integrated model. Here we have used LSTM encoder-decoder model that will translate English sentences into their French language counterparts using Keras and Python. So what encoder and decoder stands for here? So encoder is something which uses a deep neural network layers and converts the input words to corresponding hidden vectors. Each vector represents the current word and the context of word. However, decoder is similar to the encoder. It takes as input the hidden vectors generated by encoder, its own hidden states and current word to produce the next hidden vector and finally predict the next word. So now I'll be explaining the project. So what I have done, I have firstly imported all the libraries that I'll be using. I've used OS library. Also, I'll be making a model, so I've used Keras for it. I'll be using different layers, LSTM, GRU, dense layer for output. Embedding is also being done. So I've imported all the layers. For tokenizing, I've also used Keras. For padding the sequences, I've imported it as well. For simplifying the calculations, I've used NumPy. And to plot the graphs, I've used matplot.pyplot. So now I have specified some parameters. The batch size specified is 64. The epochs are 20, LSTM was 56, and all the other parameters. Embedding size I have taken 200 dimensions. Now I have declared three variables that I'll be using later on. So here I've imported dataset from my drive, and just to have a look at how my dataset looks like, I've printed number of sample input, output, and input output sentences. Just to have a look at how like what each index contains, I've just printed one data point, that is English sentence is beated and its French translation is sparse. Now I have imported pandas as well, and just because I require data frame out of my data set, and I'll be doing padding. So before doing padding, I must look at what is the maximum length of each sentence in English as well as French. So this graph basically is nothing but representation of the maximum length of each sentence. Now I have done some tokenizing. So tokenizing is basically I have uh, like every word now is mapped to a token. Now, after doing tokenizing, I'll be doing padding. So padding is done somewhat like this. We assign zeros to the words which are not there to just to equal the number of the size of each sentence. So now after doing padding and tokenization, I just wanted to look at how my uh, output looks like after tokenizing. So this is what I have done. Okay, so this is how the padding outputs look like. That is, it has added number of zeros so that all the sentences are of equal length. And in tokenizing, like the SOS word has been assigned 2 token and this one has been assigned to 6.5. So this is how our output looks like. Okay, so now I have imported some NumPy for some calculation. So now I have done word embedding. So we always have to convert our words into the corresponding numeric vector representations before feeding it into any deep learning model. And we already converted our words into numeric. So we'll be doing like word embedding. So here the embedded that I'll be using is GLOVE, that is global vectors. So it will be doing the embedding to 200 dimensions. So from my drive itself, I have taken this dataset for the purpose of embedding. So after doing embedding, this is how embedding matrix looks like. This is how it looks like. And after doing embedding, we will start creating the model. So firstly, we'll begin with the embedding layer. So the embedding layer is defined as the first hidden layer of a network, and it must specify three arguments. These are input dimensions, that is this, and then we have output dimensions, and then we have input length. So after embedding, the next thing is we need to do is to define our outputs. And as we know that the output will be a sequence of words, we can just have a look at how the output will look like. So these are dimensions of the output, and this is nothing but number of inputs, length of the output sentence, and the number of words in the output. And to make predictions, the final layer of the model will be a dense layer. Therefore, we need the outputs in the form of one hot encoded vector. Since we will be using softmax activation function at the dense layer. To create such one hot encoded output, the next step is to assign one to the column number that corresponds to the integer representation of the word. And this is what I have done here. So now the next step is to define the encoder and decoder network. The input to the encoder will be the sentence in English, and the output will be hidden state and cell state of the LSTM. So this is the encoder, and now the decoder. The decoder will have two inputs, that is the hidden state and the cell state from the encoder and the input sentence, which actually will be the output sentence with a token appended at the beginning. So, and now after defining encoder and decoder, we just have to compile our model. So I've specified that the optimizer that I'll be using is RMS-prop, and the loss will be categorical cross entropy, and the metrics to judge our model will be the accuracy. So this is the summary of our model, that is number of parameters it has, and other such things. And this is the plot of our model. So I'll be using a callback for early stopping just because I want to utilize my resources well. So I've used early stopping, and this is and I have just trained my model now for 20 watches, but it stops early, and the accuracy comes out to be 74% for the testing and 78% for the training. So now, just to plot the model loss and model accuracy, I have saved the weights in this. So now I've plotted the loss. This is how model loss looks like. It is constantly decreasing, and this is my model accuracy. So after measuring the accuracy and loss, what we need to do is to test the machine translating model. So for this, we have to follow the 4 steps. First, encode the input sequence. Then we have to run the decoder using just the start of sequence. Here I have done this. Then we have to append the character predicted and repeat the process with the previously predicted character token as input and update internal states. Now we want our output to be a sequence of words in the French language. To do so, we need to convert the integers back to words. And this is what I have done here. Now we will create new dictionaries for both inputs and outputs where the keys will be the integers and the corresponding values will be the words. Now we want to see that how our model is translating. So for that, we have make this function that is to define translate sentence, and this is the real application of our model. Now I have taken a random sentence and look at its translation. So there is one input sentence which is in English, and it is the actual translation of it in French. And this is what our model is able to achieve. And this is one another example of how our model is performing in this task. So this was neural machine translation, which focus on translating an English sentence into the French sentence. Thank you.